Good morning, students. We are resuming with our topic of ultrasound, and this is the last time we are talking about this with a few practice questions. And one question that I have selected for discussion is the one I have given you in the exercise. So it will be helpful because the idea is to give you some hands-on experience, so you see how that formula is used, how we put values in it, because there are certain mathematical functions in it which needs to be understood, so you easily handle that formula in the exam. There is a question in the exam, and most of the time this is what they ask about ultrasound when they ask you to calculate a few things. Reflection coefficient. Reflection coefficient, as I introduced, was Z2 minus Z1 squared divided by Z2 plus Z1 squared. And you remember Z is for acoustic impedance. One thing they have asked more than once is, what is the significance of the value of acoustic impedance of a particular medium in relation to the reflection coefficient? Which means if this is the boundary separating two media with acoustic impedance Z1 for this medium, medium 1, let's say, medium 1, which could be air, which could be muscle, followed by some other medium. Z2 is medium 2, of course. And when ultrasound is made incident on the boundary, how much gets reflected is IR. What gets transmitted is IT, and this is the incident intensity I. This I have already discussed with you. What we are understanding now is, what is the significance of these two values to decide how much will be reflected back? Because if amount of the reflected intensity is more than a certain allowed value, then a meaningful image will not be possible, because most of the incident radiation is reflected back into the same medium. So naturally, we will require most of the incident radiation to transmit through to the next medium. So a reasonable quantity goes into the body and then it gets reflected, and only then a meaningful information will be possible. You can see what happens to the reflection coefficient alpha, which means how much will be reflected back, what fraction of the incident intensity will be reflected. It depends on the difference of these two. If they are very different numbers, this is, for example, very large number compared to Z1, then this number is naturally will be large. Alpha will be large. That means reflected intensity, as I told you, alpha is basically IR over I. So reflected intensity will be very large. The fraction of the incident intensity which comes back into the same medium will be very large if this difference is large. So as I said earlier, sometimes we do not apply gel and we use the transducer. We bring that transducer in contact with the human body to make the ultrasound image. Most of the incident radiation is reflected back into the same medium. That means air. But as soon as we apply gel on the body, this medium will not be air in that case. This will be considered that gel, and the difference of these two will be very small then. Therefore, the value of alpha will be very small. Therefore, the reflected intensity will be very small. That means most of the intensity, almost 99% of it, will be transmitted into the body. So that will cause a meaningful image. So one thing that they often ask you to calculate is this quantity. The second quantity that they ask you to calculate is, let's say a medium has a certain thickness, and that thickness is often given, and there is a transmitted intensity, and what is the value of this transmitted intensity when it reaches the other end of this medium. For this purpose, I told you we use this formula: I is equal to I naught E minus mu x. This is the transmitted intensity, so I denote it by I naught, the original intensity upon transmission. And this is the intensity that gets to the other end of that medium. This simply means how much will be attenuated, how much will be the loss of the intensity as it reaches this end of the medium. Obviously, it depends on two factors. One is the type of the medium, which means the value of absorption coefficient or attenuation coefficient. So often they give you the value of absorption coefficient of particular medium and the length or thickness of the medium through which the radiation is passing. So if I multiply these two and use them in this formula along with the original intensity, I immediately get the value of intensity that I have at the end of that medium. I apply these two formula on a question, and the values of mu and z are given for these two media. This is muscle and this is bone. For muscle, the value of acoustic impedance is 1.7 into 10 raised to power 6, and the units are kilogram meter square s minus 1. These are given along with the value. The units are given. Value of absorption or attenuation coefficient mu1 for muscle is 23. The value of acoustic impedance for bone is given. It is 6.3 into 10 raised to power 6 with the same unit, kilogram meter square s minus 1, and attenuation coefficient for this medium, which is bone, is given 130. So I know the value of z and mu for both media. The first thing they want us to calculate is the fraction of the incident intensity that reflect back into the same medium. If it is incident here, of course it enters here. If it is muscle, it will enter here first, but whatever amount enters it, what fraction of it reaches here, we'll calculate it later, but whatever arrives here, it will be partly move on to move into the next medium, bone, and part of it will be reflected back. So we are basically calculating this amount, IR over I, and this is actually the value of intensity that arrives here. So what is incident at this boundary? Partly it gets transmitted into the next medium, bone, and part of it is reflected back. Now I don't know what is arriving here because I don't know what was the original intensity that we started with here. But without these numbers known, we can calculate the fraction of the intensity that reflected at the boundary. Without knowing these numbers, it is possible. How? Because we know the values of the acoustic impedance. So if I know the acoustic impedance of this medium, if I know the acoustic impedance of this medium, which is bone, I can calculate alpha, which will be the reflected coefficient for this particular boundary separating muscle and bone. So without knowing what is the original intensity that we started with, what was the value of it that arrived here, I mean no attenuation is calculated at this stage yet, but even without knowing these numbers, we are able to calculate this fraction. So you see, we can know this alpha using these numbers. So 6.3 minus 1.7 square divided by 6.3 plus 1.7 square. Of course, this will be the same in the two, so it will get cancelled. So if I simplify this, I get 0.33 as the answer. That means whatever intensity is incident here, 0.33% of it will be reflected back into this, and the remaining one, 67%, that will get transmitted into the next medium, which is bone. Now, the next part in this same question is, what is this value of intensity in terms of the original? Now, I don't know what is original, but let's say it is I naught, and naturally it will get attenuated by the time it reaches here. So we can calculate this intensity in terms of this intensity if I know the absorption coefficient of this medium, and now I'm talking about this formula actually. So let's see how this formula is applied. Let me erase this because we have done with this one. Now, assuming that we started with I naught, I want to know what is I over I naught, which means what is the fraction of the original intensity that arrives here. So I over I naught is equal to E minus mu x. So basically this is the formula that I have written in this form. So fraction of the intensity that arrives here is E minus. Now mu will be, of course, of this medium, which is 23. So 23 multiplied by x, which is written, which is given in the question. The thickness of muscle is given to be 4.1 centimeters. So 4.1 centimeter means 4.1 into 10 raised to the power minus 2. So if you are using a calculator, a scientific calculator of course, there is a function that appears on the screen if you take this calculator to the second mode. You change the mode of it. Usually that mode is given at the top of the calculator. I should have brought the calculator in the class so I could show you, but I'm sure you are familiar with this. There is a function that appears as this, and there is x written here. So when you shift the mode, this function appears on the screen, and then you write all these values here, and the product, whatever the product is, there is a number here with, of course, a negative value. So whatever this negative value you have as a product, your answer will be 0.39. which simply means that 39% of this incident intensity will be reaching here. The rest will be lost. So gradually the intensity which was transmitted from outside of the body is taken original value, and what fraction of it is reaching here is calculated using this formula. So these are two independent calculations. But what if they ask you the intensity that is arriving here, and this time they will ask you the intensity in terms of the original one. So I don't know what is the value of I naught, but I can express the intensity that I'm receiving at the surface of the muscle after it gets reflected from here. So after it gets reflected from here, it is reaching this boundary, the boundary of the muscle. What if they ask you to calculate this? So let's have a look at this. This is the last part of this question. What is the intensity that is reaching the surface of the muscle? First, I have calculated the fraction of the intensity reflected at the muscle bone boundary. This is the reflection coefficient of the muscle bone boundary, number one. This is the fraction of the intensity arriving at muscle bone boundary. This is reflected from muscle bone boundary. So there are two quantities we have already calculated. Now the third one is calculate the intensity in terms of I naught, that is reaching back at the boundary of the muscle, I mean, this is the boundary of the muscle where we started. This is the boundary where muscle is separated from the bone. So this is one boundary, this is the one where we started, and they are asking this time what is the intensity which is coming back here. So naturally this is important to know, because we need to know what strength is coming back of the signal. The transducer makes use of it and converts it back into the voltage pulses, and then this information is given to the sensors, and they make use of this information to make that image that we see on the screen. So what percentage is arriving here is important calculation, because we want to know at least what strength we have coming back. So if you understand what reach is here, and you also understand what fraction is reflected back, it is easy now to calculate what will be available back at this surface. We know that 0.39 I naught is the intensity which is arriving here. 0.39 is the number I have already calculated. So this was I over I naught. That means the intensity that I have here, which is reaching through this, is 0.39 times the original intensity. So this number I know. But what fraction of it is reflected back? For this, we simply multiply it by 0.33. That means this is the intensity with which we are starting now. So what is reflected from this surface is actually this 0.39 times I naught multiplied by 0.33. So this is the amount of intensity in terms of original intensity I naught that is reflected from this part, muscle bone boundary. What is arriving here is simply E minus mu x. Because this is the same mu and this is the same x, that means we expect all this to be the same number 0.39 that we have calculated earlier. This. So this all becomes 0.39 squared times 0.33 I naught. And when I simplify all this, it becomes 0.050 I naught. So this is the intensity that is received here, which means this is 5%. So what I get is 5% of the original intensity after it gets reflected from here. So there are various numbers involved here. Go through this carefully. You have this question in the worksheet. Try it on your own. And then if is there any difficulty, we can discuss it even in the next lecture. Another question that I would like to discuss is similar nature, but in a slightly different way they have asked. Let me quickly discuss that question as well. Again, there is a data given for various media in which we have blood, we have bone, and we have muscle. And the values of absorption or attenuation constant, attenuation coefficient mu is given. For blood it is 2. This is measured in SI units. This is measured per meter. This is 130 per meter and this is 23 per meter. How much of the energy is lost per meter? That is the absorption coefficient. How much of the intensity is absorbed per unit length of that medium when it moves through it. The question is, what is this fraction equal to? This is the fraction of the intensities that pass through the same length of different media. For example, this is the length of the section of the body in which we have blood only. Ultrasound enters this part and it gets transmitted through this and reaches the other end. Let's take the length 4 centimeter for this particular thickness of that section of body which contains blood only. So what is the intensity that transmits through 4 centimeter of this section? So intensity that transmits through blood, to the intensity that transmits through muscle. We take a section of the body which is a muscle and we make sure that its thickness is exactly same, 4 centimeter. What will be this ratio equal to? So the formula, if I start with the same original intensity I naught minus mu x, and for this same I naught E minus mu x. Now original intensity is same for the two, it gets cancelled. The values of mu are different. So I write this as mu1 and this as mu2. And when I simplify this, I can write all this as E minus mu1 plus mu2, and this x is taken common if this x is same for the two. So this is the simplified form of this formula that we can use to calculate fractions whenever they ask, because they frequently ask questions like this, that if we have different media, they have of course different values of the absorption coefficients, but what if they have the same thickness? We want to calculate the fraction. We want to know what is the intensity that transmits through one type of medium to the intensity that transmits through another type of medium. So this is the formula. So I use the values that is given in the data, E minus 2, because for blood it is 2 and for muscle it is 23, so plus 23, and x is 4 centimeter, so multiplied by 4 into 10 to the power minus 2. When I use the same technique, I shift the mode and then I see a function on the screen which is usually with the natural log. So this appears E, this is minus 21 multiplied by 4 into 10 to the power minus. So this all simplifies to 0.92. All this product, which is the power of this exponential function, is 0.92, and this simplifies to 2.5. So fraction of the intensity that transmits through blood to the intensity that transmits through the muscle, if the original intensity is same, if the thickness of the two sections of the body are kept same, this fraction appears to be comes out to be 2.1. So this 2.1 simply shows that the value of this intensity will be larger, naturally, because the absorption coefficient of blood is smaller. So smaller attenuation will result through that section which contains blood only, as compared to that section of the body which is muscle. And a similar fraction is expected if we have intensity that transmits through muscle to the intensity that transmits through bone. So again, that will be a much larger number than this if I write muscle hair and I write bone hair, or I write blood hair and bone hair. So a much larger number is expected here using the same logic. So this is all from the point of view of discussion. I selected these two questions because there are questions of this type in the exam, and there are many other questions which are conceptual type. So the idea is that you need to go through the literature. You have books available, there are a lot of information available on the internet. When you go through all this, you will be able to answer those questions which do not require any mathematics. They simply require you to use your concepts of the ultrasound, how they are generated, how they are used, and what are some of the basic principles attached to this. So this you can do on your own. We can start a new topic tomorrow. That is electric fields. So thank you for today.